kind of a lot going on at once. So I'd like to kind of give a summary here to start. All right, so this is kind of to frame everything that we're doing, because it's kind of going to feel like, well, we're over here, but then we're over here, and then we're doing this. So I want to try to kind of organize what we're doing right now. Okay, so what are we doing? Given an exact accumulation, determine exact rate. That's the big picture of what we're doing right now. It's the reverse process of what we spent doing in February and the first half of March. Okay, we're doing the reverse now. Given exact accumulation, and better than that, we want to determine closed form exact rate. When we were on the other journey, okay, and please, I hope your attention is to listening and not writing. Okay, we really have to frame your thinking. Take notes, but don't let that mean you're not listening. Okay, so when we were on the forward journey and we were getting accumulation from rate, the goal or the end of that was the integral function, exact accumulation. But that was open form. Okay, so when we do this reverse journey, we can do better than that. Okay, we can get closed form exact rate from accumulation. Okay, so that's what we're doing. So on the forward journey, yes, we got to exact accumulation, but it was this open form integral function, which is less convenient. You need technology to spit out values of accumulation for you. But the most convenient thing is to have a closed form. So in this journey, we're going to determine closed form exact rate. Okay? And so we talked about approach number 2, and that led us to this rate of change function. This rate of change function, we said it was the rate of change of the function f with respect to its input x. Okay, and so this rate of change function is kind of the centerpiece of everything we're doing right now. Okay, does it give approximate or exact rate of change? Depends on h, right? If h is not small, it's approximate rate of change. But if we took the limit of that as h approached 0, or if we say h is super small, then it's exact rate of change. Okay? All right, and so now you've seen in your homework, we're seeing with some algebra, this rate of change function applied to a specific accumulation function can give a closed form exact rate. For instance, we saw that the accumulation of area of a square, we found that when we used this, when we used the rate of change function, did some algebra, we got a closed form rate of change function, 2x. Okay, 2x. Okay, so when we generalize that process, it's going to lead to rules or shortcuts for finding closed form rate of change, and that's what this is what the mastery is about. The mastery test is about learning these shortcuts or rules that immediately give you closed form exact rate of change from accumulation. Okay? All those rules, though, come from the rate of change function. So whenever we derive a rule, we'll always start with the rate of change function. Okay? This is the key. This is the centerpiece to it all. This is what we trust. Okay? Lots of you struggled with getting right answers on web work. Why? Because you had lots of algebraic steps, and you're bound to make a mistake, right? And so many of you made many mistakes, and so you weren't getting the right answers. Well, this rate of change function we trust, right? So we don't always trust our algebra, but we can always trust this. This will always give us the correct rate of change. Okay, but in this the whole deal of this, we can never lose sight of the meaning of rate of change. Okay. So I hope that kind of frames or organizes what's going on right now. So we've got this rate of change function. When we apply algebra to it, we can get exact closed form rate of change, and we're going to start developing some rules accordingly. But we always want to, so we don't want to get so bogged down in the algebra that we forget what rate of change is, which is the most important thing. What is rate of change? Yes, please.
Are we recording this?
Yes. Thank you. Okay, so let's talk about meaning here. So here's a function g. What's the approximate rate of change of g when x equals 1 according to this linear piece? Could you find that? So I want to approximate the rate of change of g of x when x equals 1. Go. Everyone should be able to do this. Can you approximate the rate of change of g when x equals 1 according to the way I've set it up here? Okay, so not that you would need h. You don't need h to do this. But what would h be in this case? 3 would be the x change in x, right? So you don't need that to answer this question. But if we're thinking about our rate of change function, h would be like 3, right? So this is h equals 3, and you should have gotten negative 2/3. Did you get negative 2/3? Yes. Change in y over change in x is an approximation for this rate of change right here. The rate of change, there's negative 2/3. Okay, how can I make the approximation better? And h smaller would mean, what about this second point? So we got that first point, we're using a second point. What about that second point if h was smaller?
It would be closer to the first point.
It'd be closer to the first point, so kind of like this?
No. Yes.
So let's do it again. We're going to get a better approximation of the rate of change at x equals 1. Go. We want a better approximation now. What is h like here? What is it? Tell me what h is like here.
0.05.
0.05. Okay, don't worry, I got you covered. So what are we going to do? We're going to do the change in y over the change in x, right? I got you covered. This is going to be negative 1.311. So we used h equals 3, and we got a first approximation. But then I made h much smaller, 0.05. We're focused up here now. And we got a much better approximation for the rate of change, negative 1.311. Okay, we good so far? So let's do that again. Do it for h of 0.05, but at this point now. So now x equals 4, and h equals 0.05. So this is the point here, this is the point 4, 2. And this is this point here. So do you know how you would calculate the approximate rate of change at x equals 4 for an h of 0.05? You should all be thinking that you would take the change in y. So you would take change in x. You would take the 1.983 minus 2 over 0.05. Okay? So that first one we did before was the rate of change of g at 1, at x equals 1, or an approximation for it. And so now this is the rate of change of g at 4. And when you do the change in y over the change in x, you get negative 3.33, or about negative 1/3. Okay, so what do these numbers mean? What do these numbers mean? So look at this number, negative 1.3. What is this number? Is this about negative 1/3 or negative 0.33? What do those numbers mean? Tell the person next to you, and I'll keep taking attendance. Go. Mitchell Mundy. Brianna Murray. Brianna Murray. Sylvia. Maya Navarrete. Vanessa Navarrete. Tammy, no. Okay, we'll keep going, little by little. All right, what do these rate of change values mean? So, yes, they are the rate of change. What do they mean? So, what is the rate of change?
Oh, so it means that the rate of change with respect to the input, if we're talking about 1, then the rate of change when x is equal to 1 is going to be negative 1.311.
And what does that mean that the rate of change is negative 1.311?
It's decreasing.
Okay, it's decreasing. She says decreasing because it's
Negative.
okay, good. So if it's negative, it's decreasing. But what about that value, negative 1.3? Yeah.
It's the accumulation of that.
It's the accumulation at that point.
It's the rate of accumulation.
Is it the accumulation or the rate of change of accumulation?
The rate of change.
Rate of change of accumulation. But what is that? What is that?
How fast
Okay, hold on a second. Anybody? Somebody new? Yeah, you had your. Yeah, now you're getting it right. Okay. Yes.
Okay, it's the current rate of change of g in respect to x.
But what is that? What is rate of change? You keep saying it's the rate of change. Yes. Go. How fast it's accumulating. Good. All right. So it's how fast it's accumulating, and so remember that that is essentially delta y over delta x. And what is a quotient? Remember from week 1. What does a quotient mean? Relative size, right? So it's the relative size of the change in y to the change in x. Or, and what does that mean? That is how fast y is changing in relation to x changing. Okay, so up here at 1, let's just erase a little bit. So up here at 1. When x changes a little bit, when we get a little change in x, how much does y change? How much does y change? Okay, you can do better than that. Someone said k delta x. Well,
It's actually
be specific. How much does y change? How much does y change when x changes a little bit at x equals 1? What's that? Negative 1.311 as much as x, right? So people said k delta x, but right, we've got k. We've got a good approximation for k. So y is going to change negative 1.3, about negative 1.311 times as much as x. So it's this number, negative 1.311, is telling us how much y changes for a change in x. So it's whatever that change in x is, y changes like 30% more than that change in x, right? Negative 1.311, or a moderate to fast change in y downward from what it was before. Okay, so this number is telling us the relative size of the change in y to change in x, or how much y changes relative to a change in x. And then what happens down here? And so now when we get down to x equals 4, what happens now? We get a change in x. How much does y change now for a change in x? 1/3. It decreases by 1/3 as much. So I'll just do that, just it's easy to write. Because that's about negative 0.33. Delta x, sorry, delta x, thank you. So this number of rate of change tells us how much y changes relative to a little change in x. And what's happening? So that rate is changing. That rate is changing. At first, the y is decreasing faster, more rapidly, at this rate of negative 1.311 relative to x, change in x. But then later, when we get to x equals 4, now how is y changing? it's decreasing less rapidly, right? It's only, now a change in y is only a third of what you would take for a change in x. So there's so much information packed into this number. It's how much y changes relative to a change in x. Okay, and so, right, so y is going down, heading down more rapidly, and y is heading down less rapidly, and this number is telling that story. These numbers are telling that story of heading down at a certain rate relative to a change in x, and then heading down less rapidly or less quickly. In this case, it's going down 1/3 as fast as x increases. Super important. Maybe the most important thing of all semester, understanding what this number of rate of change means. The relative size of the change in y to change in x, or how fast y is changing in relation to x changing. Okay? And then, so what are we doing? And this rate of change function then is a function of rates, right? So we plug in any x, and it tells us, for any x, it tells us what that number is, the current value of relative size of change in y to change of x is. So it's the rate of change function gives us a whole function of these values, k values, right? Like k. Okay. And we'll just keep reminding, we'll just keep looking at this from different angles as we go. Even as we're doing all the algebra, we'll just keep taking little detours to review this. Okay, so that function is actually, the one I just showed you, is actually 12 over x plus 2. That's what that function was, that downward curve. And now I want to find a closed form. So we were just approximating with h of 0.05, right? Now I want to find a closed form rate of change for this function. How do I start? How am I going to start? Now I actually want to get a formula that I can plug in 1, and it'll give me that rate of change. And I can plug in 4, and it'll give me that rate of change that we found by approximating. How do I start? Mm-hmm. What will it be?
So we 12 over x plus h. Is it right or no?
Okay, so yeah, you got the right idea, but let's write it out in terms of g first.
Okay.
So we'll do it in terms of g first. So what's the overall structure of our rate of change function? Change in output over change in input. This is our trusted rate of change function. We know this gives approximate rate of change for a width interval of h at any value x. And all we need to do at the end is make h small, and we got exact rate of change. Okay, so what is g of x plus h? 12 over x plus 2 plus h, right? No, the input is x plus h, and this function says take 12 over the input plus 2, right? This says take 12 over the input plus 2. Our input is x plus h, so 12 over the input plus, that should be a 2. Minus?
12 over x plus 2.
Yep.
And all this is over h.
There's our rate of change function for g. That's our rate of change function for g. Okay, so I'm going to go fast. If I lose you, watch the video. Okay, I don't want to get bogged down in algebra in class, so I'm going to go fast. We need to subtract. We need a common denominator, right? The common denominator will be the product of those two. So we're going to have x plus h plus 2 times x plus 2 would be our common denominator when we subtract these two fractions, right? And so then what will we have to do to the first fraction to get that common denominator? Top and bottom by x plus 2. So we'll have 12x plus 2. And what will we have to do to the second one to get the common denominator? X plus h plus 2, top and bottom. So minus 12 times x plus h plus 2. So I did two steps at once there. I found a common denominator, and I subtracted those fractions in the numerator. And that whole thing is over h. Okay, so now I can simplify this numerator of the numerator will be, I got a 12x and a minus 12x. I got 24 and minus 24. So all that's left here is negative 12h. And I'm just going to leave this just as it is. I'm not going to multiply that out. You can thank me later. And that whole thing over h. Okay, now look, I've got just h here. So I got it like h in the numerator, h in the denominator. Bye-bye. H over h is 1. They're gone. So we end up with, can I fit it over here? Negative 12. That's right. X plus h plus 2. X plus 2. Okay, so that's the approximate rate of change of the function g. It's the approximate rate of change of the function g. And as long as h is not small, that's an approximate. But how do I get it exact? So if I apply the limit to this as h approaches 0, then what do I get? Negative 12 over? Yeah, so this essentially becomes x plus 2 when h gets very, very small. So now I have two x plus 2's in the denominator. And so essentially we got negative 12 over x plus 2 squared. Okay, so look at this. Exact rate of change in closed form. Just by doing some algebra on our rate of change function, we get exact rate of change in closed form. And so for h of 0.05, we calculated, remember we did an approximation for 0.05 of negative 1.311. So let's see what is the exact rate. What are we going to do? Plug in 1 into our exact rate function. So when x equals 1, negative 12 over 1 plus 2 squared, or negative 12 over 9. What is negative 12 over 9? Negative 1.4 negative 1.33. So with h as 0.05, pretty dang good approximation that we got before. X equals 4. We did that with the graph, right? So negative, it's going to be negative 12 over 36, which is negative 1/3, and we got negative 0.330, right? So at h equals 0.05, we got good approximations, but now we're talking exact numbers. All we do, so here's the beauty of closed form. You just plug in x and it spits out the answer, right? You can avoid setting up the line and getting the approximate rate and making h small. Now this is the beauty of closed form. You just plug in x, it spits out the rate. Plug in x, it spits out the rate. That's a closed form function. Okay, questions on that? Does it make sense? Can I erase this page?
Yes.
Okay, so now, given any exact accumulation function, say g of x, its exact rate of change function is called the derivative. That's what the derivative is. The exact rate of change function for a given accumulation function. So, in our last example, negative 12 over x plus 2 squared is the exact rate of change function for the function g of x equals 12 over x plus 2. And because it's the exact rate of change function, therefore negative 12 over x plus 2 squared is the derivative of g. So by doing that algebraic process, we found the derivative of g. Okay, so notation for the derivative. So here's one notation that we'll see. So if it's the function g, then it's d dx of g. Here's another notation you'll see for the derivative, g prime. And those both mean this, right? If it's exact rate of change, it's the limit as h approaches 0 of g of x plus h minus g of x over h. Okay, there's one more form that you'll see often, and that's because the output is often y, you'll also see, I'll write it up here. You'll also see this, dy dx. That's another notation for the derivative of the function with respect to x. If you're using y to represent outputs of the function, which is conventionally what we do, you'll also see dy dx. Okay, so what about our rate of change function? The notation r, the rate of change of g with respect to x. Does it mean the derivative? Is it the derivative or not? What's that? Depends on what the size of h is. Remember we said that's our flexible only for extremely small values of h. So we said this is what we built, the rate of change function, we said was flexible. If we take the limit of that as h approaches 0, then yes, it's the derivative. But if h is non-small, it's an approximate rate of change, and it's not the derivative. So the term derivative is specifically reserved for, okay, so this is the exact rate of change now, always. And so these notations are for derivative. The dy dx, d dx, g of x, g prime of x, which means this. And then, but our rate of change function, we allow it to be flexible for us because it's nice in different situations. It's nice to have it be approximate, and then just let h get small, and then we know it's exact. Okay. But all of them, here's the key, all of these are read as the rate of change of g of x with respect to x. The rate of change of g of x with respect, all of them are that. Whether it's derivative or a rate of change function, the rate of change of g of x with respect to x. Okay, any questions? All right, so we're gonna start building rules. So like using the rate of change function, we can just take a general case like this, x to the n. If we apply the rate of change function and we work it through with the algebra, then we'll get a general rule for all functions that are x to the n. So let's derive this one. And so first a reminder, x plus h squared is not x squared plus h squared. There's a middle term, right? And if you raise the power of that, don't try to write all this down. If you raise the power of that, you get more middle terms. Every time you raise the power, you get more and more middle terms. So x plus h to the n is, depending on what n is, you're going to have multiple terms. And what happens with each one? Look, so the first term is always x to the n, and the last one is always h to the n. And then you're going to have a term where x is one less power, and then h is one greater power. And then as you move this way, in each term, the power of x goes down one, and the power of h goes up one. So you have every combination of power of x and power of h that sum up to n. So x marches down in power, and h marches up in power until you get to h to the n, and no more x's. Okay, so that we're going to need that little rule to derive this formula for the rate of change of x to the n. Okay, so here we go. Let's do it. So how are we going to start? If we got f of x equals x to the n, and we want to figure out what its rate of change is, what is our first step? Always. How can we, what's our trusted rate of change form? F of x plus h minus f of x over h. When we derive these rules, we will always start with that because this is our trusted rate of change formula. Okay, what's f of x plus h? X to the n plus h. Is that what it is? X to the n plus h. No. The input is x plus h. This function says take the input, raise it to the n. So what will it be? X plus h to the n. Okay? So the f of x plus h will be x plus h to the n minus x to the n over h. Well, this is what I just showed you on that previous screen. It's that long thing that expands out depending on how big n is. You get lots of middle terms. So here's that, okay? So that was in parentheses. It's just what I showed you on the previous page. The power of x starts at n and marches down to 0, while the power of h increases by 1 each term until it's h to the n. Okay, what do you see? What can we do with that numerator now? Not yet. So yeah, eventually. So see, I got x to the n at the beginning and minus x to the n at the end. So what about those two? 0. Bye-bye. X to the n minus x to the n is 0. So we're left with this. What do you notice about every one of those terms? They have a h. We can factor out an h. And this is what's left when we factor out an h. This isn't hard. This isn't hard. It's just a lot of symbols, but it's not bad. We're going to factor out an h. And then now what do we have? H over h. And now we're left with what's in the parentheses on the top. And we want exact rate of change. So what are we going to do? Let h get very, very small, or 0. And so what will happen, notice that all those have h's. Every term except the first one has h's in it. So when h gets very, 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 very close to 0, very small, those are essentially our 0, and we're left with n x to the n, just that first term, n x to the n minus 1. So here is a closed form rule for the exact rate of change when your accumulation is x to the n.
That was weird.
Even the ghosts want to know calculus, I guess. All right, here we go. So the rate of change of the function of f of x, if f is x to the n, then its rate of change is n x to the n minus 1. And so visually you can think about it as you take the exponent and you move it down in front to be the coefficient, and then you reduce the exponent by 1. And that gives you the exact rate of change function for x to the n.
Can we say it's 7 times?
Yeah, keep practicing rate of change of x, though. Yeah. But yes. Okay, so therefore, we got our first. This is our first rule, and this is probably maybe the most common one you're going to see. So that when f of x is x to the n, the exact rate of change function is n to the x minus 1. So some real quick examples. So if you have x to the 8th, what's the exact rate of change of x to the 8th? So it means it's gonna be 8x to the 7th. Move the coefficient in front, reduce the power by 1. That's what all that algebra told us, was that the exact rate of change function would be 8x. So remember our square function. Okay, be careful. So lots of times I see students, they'll write x to the 8 equals 8x to the 7th. What's wrong with that? They're not equal. You have the accumulation function. You're finding the rate of change function. So they're not equal. They're two different things. So that's why I put an arrow. So I'm just using a shorthand notation. Given that accumulation function, the rate of change function, in this case, is 8x to the 7th. So remember what we found for x squared. We found it was 2x, but now we've got a shortcut rule. Move the 2 in front. 2x to the 1, which is 2x. Okay, this rule works with negatives, fractions. So how about negative 9? Negative 9. Now you've got to be literal. So you truly still reduce it by 1. What's 1 less than negative 9? Negative 10. So it truly, you still subtract 1 even if the power is negative. And then we could do, say, yeah, x to the 1/3. It'd be 1/3 x to the, so it'd be 1/3 minus 1. 1/3 minus 1. Reduce it by 1. Okay, try this one. So now, in its current form, you can't apply that rule, but you can change it. You can change it to fit x to the n. So that's why you do it first. So this is truly equals. This is truly equals. This equals what? X to the. So you got to know your powers of exponents. So those are truly equal, right? If you have 1 over x to the positive 14.3, that's x to the negative 14.3. And now I'm going to find the rate of change. Negative 14.3 x to the. Subtract 1. So the rate of change of 1 over x to the 14.3 is negative 14.3 x to the negative 15.3. So sometimes you have to do a little algebra before you apply the rule so that your expression fits the rule. This doesn't fit the rule. Okay, you can't do 1 over. The derivative of this is not. Let's do it in red. The derivative of this is not 1 over 14.3 x to the 13.3. Right? That's different than this, right? That's much different than this. And that's not right, because the rule is not 1 over x to the n. It's x to the n. So you need to get it in that form first, and then apply the rule. So you can't do this. It doesn't work. Okay. All right, so here's some other notations for the derivative, right, that I showed you before. So that's our derivative. Okay, and we'll call this the power rule. This is the power rule because the original function is x to some power. So this is the power rule. So it gives us, so think about all that work we did to get from accumulation to rate of change. Now with this shortcut, it's like, boom, within 2 seconds, we have an exact accumulation function, and 2 seconds later, we have an exact rate of change function. And that's because of the hard work we did to get there, right? All that algebra in between. Okay, so let's do some other rules here. Ready? Here we go. Accumulation function f never accumulates any changes in its value. In other words, it's a constant function. What is its rate of change? Some people are saying 0. Do you agree with that? The rate of change, how fast it's changing. If it's not changing, how fast is it changing? 0, they're right. Okay? Can you prove it? So, prove it. You've got a function f. Prove that if it never accumulates a change in its value, what's its rate of change is 0. Okay? So we can, the given situation we can frame this way, that the accumulation never accumulates any change, right? It's a constant. So now, show mathematically that the rate of change is 0. Can you do it? I think you had one in the homework like this. Okay, I'll take some more attendance.
Within x, I replace x plus h to the power 0 minus, times c, subtract.
Okay, yeah, that's right. That's right. Okay, so we're going to use, she's using the rate of change function. What is f of x plus h? This function says no matter what you input for x, the output is always c. That's what it says. It doesn't matter what you input for x. You always get an output of c. Therefore, if you input x plus h, what do you get? And if you input x, c. That function says no matter what you input for x, your output is c. So whether it's x plus h or x, you always get c. And so what's the rate of change function? 0. There it is. What's that?
Just talking about.
Okay. You good?
No. I'm trying to figure out where c comes from c.
Because this is a constant function. The definition of the function is that no matter what you input for x, you always get a constant.
Right.
It doesn't change. So here's another different input. You're going to put input x plus h. What does that equal? Doesn't matter what you input into this function, you always get c. So if I input x plus h, I get c. If I input 5, I get c. If I input 100, I get c. So no matter what I input, I always get c. That's what that function says. Therefore, c minus z is 0. Rate of change is 0. Okay, constant multiple. So we got two rules now. We got a power rule and a constant. Power rule and a constant. Here's another one. At every moment in time, John has traveled 5 times as far as Mary. What can we conclude about John's speed relative to Mary's speed? 5 times bigger. So at every moment in time, John's speed is 5 times Mary's speed. All right, so if F gives John's total distance after X hours, and G gives Mary's total distance, what's the setup? So the setup is he's traveled 5 times as far as she has. So the setup of that is F equals 5G, right? Our conclusion, at every moment in time, his speed is 5 times Mary's speed. How do we write that?
5 times.
So if F is distance, what would be the corresponding speed?
The rate of change.
Rate of change, right? So the rate of change of F, then, so this was our setup. Our setup is embodied in this formula, that his distance is always 5 times as far as his. And you said, therefore, his speed is 5 times as much as hers. That's what that statement is. The rate of change of distance, John's distance, is 5 times the rate of change of Mary's distance. So using the other notations, right? So the rate of change, these all mean the same thing. All these mean the same thing. And we're going to, like I said before, we're going to read all of these as the rate of change of F with respect to X is 5 times the rate of change of G with respect to X. All of those are read this way. So don't say D's, don't say prime, although that's the common thing to call this is prime. And we say df dx, dg dx, okay? But we should practice reading all of these as the rate of change of F with respect to X is 5 times the rate of change of G with respect to X. All of those communicate that. Okay? And so here's the rule. So we didn't actually prove this one using the rate of change function, but this is the generalization of what we did with the speeds. If F has a value that's C times as large as the value of G, then its rate of change is C times as large as the rate of change of G. So that's a third rule. This is called the constant multiple rule. If you have a constant multiple times a function, the rate of change is the constant multiple times the rate of change of the function. That's what we're saying. If you have, basically what we're saying is, if you have a constant multiple times some function, then the rate of change of that is the constant multiple times the rate of change. So notice, you treat the constants differently. If you just have a constant, what's its rate of change? 0. But if you have a constant times another function, the rate of change, it's not 0. You hold on to that constant and you multiply it by the rate of change of the function. So when you have a constant by itself, its rate of change is 0. When you have a constant times a function, you essentially take the rate of change of the function and hold on to the constant. Take the rate of change of the function and hold on to the constant. That's what we're saying. Okay, again, the rate of change of F with respect to X is C times the rate of change of G with respect to X. Okay, so we've got 3 rules now. Here's the 4th one. The rate of change of a function, that is the sum of functions. So what I'm after is, I want to know what the rate of change, in this case, of k is, if k is the sum of 2 other functions. So our goal is, what is the rate of change of k? What is the rate of change of k of x with respect to x? So this one, I want to see if you can prove it, okay? So again, the focus is on what is the rate of change of k of x? And that's where you're going to start. So you're going to start with that. You're trying to figure out what the rate of change of k of x is. All right, so I'm going to finish attendance. All right, we're going to do it by hand. So let's go back. I thought the proof was on this slide. It's not the proof. It's just the result. Okay, so what comes first? We're going to write it out. What comes first?
R of k, Rk of x equals something else.
K of
X plus h
x plus h.
minus k of x over h.
This is, if you don't do this as the first step, you'll be off on the wrong track. No matter what k is, this is its rate of change, no matter what k is. Now we look at what the definition of k is, and we apply this to the definition. So, what is k of x plus h? What is k of x plus h? We just want to do this much. So if k of x is f of x plus g of x, then what is k of x plus h? F of x plus h plus g of x plus h. That's k of x plus h minus k of x. Made it? All over? This is, if you don't get started this way, then you'll never make it. So do you understand? We're focused on the rate of change of k. No matter what k is, this is its rate of change. Now we apply the definition to write what the rate of change function is. So notice, you see a f of x plus h and a minus f of x. Let's group those together. And you see a g of x plus h and a minus g of x. Let's group those together. So addition of subtraction, you can change the order, right? All right, now so you know when you add fractions, you have a common denominator. You just leave the denominator as it is. We'll do the opposite. We're going to split the fractions apart with the common denominator h. So it's going to be all over plus and then, if we've been paying attention and we're alert, we notice something. We think, wait a second, I know what that is. What is that? What is it? What I circled in blue has nothing to do with k. It's the rate of change of f with respect to x. That's the definition of the rate of change of f with respect to x. And this one over here? Rate of change of g. So what is it? It's the plus. So what do we find? If k is the sum of f and g, then the rate of change of k is the sum of the rate of f and the rate of g. So it's exactly the result we would hope for. That if you have the sum of functions, the rate of change of the sum of functions is just, you're going to just add up the rate of change of each individual function. So it's the most natural thing and the easiest thing we could think of. Another way to write it would be, we could write it this way. So when you have the sum of functions, you can just find each individual rate of change and add them together. That's what this rule says. And we proved it, right? So we did all legitimate, valid algebraic steps to prove that fact. Okay, questions on that? So here's all these different ways to write that. They all mean the same thing. And those are in terms of derivative, right? Exact rate of change. Okay, so here's our summary. Here's the 4 rules we've learned so far. If you have x to the n, what's the rate of change? N x to the n minus 1. If you have a constant, the rate of change is 0. We showed that that was 0. Now, if you have a constant times another function, is it 0? No. The rate of change is? The constant times the rate of change. So basically you just hold on to the constant and take the rate of change of the function. You just hold on to the constant and take the rate of change of the function. But if it's just a constant, the rate of change is 0. And then if you have the sum of functions, the rate of change is the sum of the rates of change. Again, these rules are giving us like an immediate fast track to an exact closed form rate of change function, which is super convenient because you just plug in x values and it spits out the rate of change for that x value, instead of all this work in the process that we developed. Okay, so now, here's a polynomial, p of x, and we want to slow down. So if you've done this before, pretend you never have. Okay? Pretend you've never done this before. We want to find the rate of change of p. Every single one of these rules comes into play. And so we want to apply these rules in the correct order. And so what that means is we have to look at what is the overall structure of p. That's going to be the first rule, or the rule that we apply. So what is the overall structure of p? Is it something to the n? Is it a constant? Is it a constant times a function, or is it the sum or difference of functions? Which one of those 4 is the overall structure of p? 1, 2, 3, or 4? So I'm hearing some people say 1. Is the overall structure of p x to the power? That's what you're saying. Is it something to a power, or x to some power? No, that's not the overall structure. So that would look like this. If it was number 1, then p of x would be this. X to some power. And that's not what we have. So which rule gives us the overall structure of p? 4. Okay? So our first step would be the rate of change of p is going to be the rate of change of that minus the rate of change of that plus the rate of change of that. Okay, and then when we get to the rate of change of this one, yeah, it's just a constant, so we'll do this. But the first rule that applies is number 4. Okay, so now we get to the rate of change of x to the 11th. Which rule applies to 1, 2, 3, or 4? 1. What's the rate of change? 11 x to the 10th. Minus, okay, which rule, 1, 2, 3, or 4, applies to this? 3. It's a constant times a function. And rule 3 says, hold on to the constant and take the rate of change. So it's going to be 5 times rate of change of x to the 4th. Now we apply rule 1. 4x cubed. Plus 1, 2, 3, or 4? 3. 3 is the rule that applies here. 10 times, now rule 1. And this was rule 2, right? This was rule 2. It's just a constant. So the rate of change of p with respect to x equals minus 20x cubed plus 30x squared.
That's not too bad. It goes back.
Okay. Okay. Any questions on that? So again, so we're using rules in combination now. So this polynomial P used all four of those rules. First it used, don't pack up, we're not done. First it used sum or difference. And then in each individual one, sometimes it used the constant multiple. This one used constant multiple. These two used constant multiple. This used rule number 1, just our power rule. And this was constant rule. So all four of those rules apply to finding this rate of change of P. So the cool thing about the rules is we started with a complicated accumulation function, and very quickly we got its exact closed form rate of change function. Very quickly. That's the efficiency of the rules. Okay, so I want to derive one more rule, or at least just get started on it. Oh, come on, play. Square root of x. Write the first step. Go. First step to find the rate of change of the square root function. It always starts with our rate of change function, right? So you should have gotten this. Square root of x plus h minus square root of x over h. Are we cool with that? Okay, so just watch and then look at the video. So to work on this, what you do is you multiply the top and bottom of what's called the conjugate. Okay? So the conjugate is you just change the sign, you change the minus to a plus. So you're going to multiply the top and bottom by that. And it works because it gives us a squared minus b squared, and that'll get rid of these square roots. So the numerator becomes x plus h minus x, that's a squared minus b squared, and the denominator just multiplies out. So we get our h over h is 1. And when h gets small, it's essentially 1 over square root of x plus square root of x, or 1 over 2 square root of x is the rate of change. Okay, you definitely have web work. It's opening now. There might be a little written too, but definitely web work for Thursday. Yeah.